Math 126 students. I'm going to go through, work through an old exam. We'll see how this goes, if whether I can talk about more exam in this video, but ultimately we're going to talk about exam 2. Now this covers 3 things: section 13.4, which is that little bit we did on acceleration, the tangential and normal component of acceleration. I could ask one small question on that. And then we did chapter 14, which was partial derivatives and local maxima and global maxima and applied maxima. And then chapter 15, which was mostly about working with regions and doing double integrals over regions. This is the review fact sheet. You can find this on Canvas. This is me trying to fit everything on a page. Ultimately, you need to know the basics of contour maps and curves and understanding what partial derivatives mean and how to find them. We use partial derivatives to find tangent planes. Another word for a tangent plane is a linear approximation. So those questions are basically just saying, compute the partial derivatives and use them. We talked about the concavity. Primarily, we use that in the second derivative test. You probably will have something on the second exam that involves finding critical points and using the second derivative test. And there's some logic in how that goes. For absolute or global max and min, there's a little more to do because you have to do each boundary, all that same stuff. For double integrals, to me, it's all one big idea, which is you have some integrand, some surface, and you have some region on the ground. And I broke this up into 2 steps about how to find the region on the ground, which are the given. Anyways, we've done that quite a bit. And then you have a choice of how to set it up. Do you want to do it in terms of x, in terms of y, or in terms of theta, the polar version? And we've talked about how to do that. We're not going to talk about other applications. I could ask about area of a polar region, but we're not going to have center of mass on this test. So there's the quick review. You can see it's kind of a couple big things. Typically there will be a local max and min. There will probably be one of either. I usually kind of alternate between, not every time, I'm not saying I'm going to do that, but between some sort of applied max and min or a global max and min. So probably one of those will be on there, usually on the last page or something. And then a couple questions on double integrals, definitely polar. Okay, so let's look. I have 3 old exams here. The winter 2023 I just posted. Yeah, maybe we'll start there. So here we go. Here's let's just look at this. This is winter. This is spring 2023. It should say spring 2023. Let me fix that. If anybody's looking at this later, spring is the last time I taught this. Spring. All right, whatever. So first we have a partial derivative question. I do see several people asking about this on the discussion board. Again, when someone says compute the partial derivative so if you're computing the partial derivative of z with respect to x, that implies, so I'll write this on the side so I have room to work when I come back. This implies we're thinking of z as a function of x. And it means that y is being treated as constant, but the 2 variables are z and x, which does mean when you go to take the derivative, so let's say we start taking the derivative, we need to treat this, and this is a review of implicit differentiation, but sometimes people miss this on the first go around when they were doing the homework. You have to think of it like this, and then you treat y like a constant. So this is a constant term. So the derivative, that's going to be 0 if you take the derivative with respect to x. This is going to be a coefficient, but the derivative with respect to x is going to be 1. Now I went through this in class back when we were doing this. This is going to require we take the derivative. So we're going to need the chain rule. It's going to be 12. And now we usually don't write 12z of x to the first times the derivative of z with respect to x. We usually just write 12z dz dx. When students first learn this, when they're doing implicit, they think of it as just multiply by dz dx each time. But when you get to the second term, there's actually two variables. And so you do need the product rule. Here's the first, here's the second. I'm saying a little more about this because I saw this was asked on the discussion board. So first times the second plus the derivative of the first times the second. So first times the derivative of the second, which is dz dx, plus the derivative of the first times the second, which is z, plus y. That's the y is coming from the derivative of that. So that's it. This question is saying, what is the partial derivative at 2, 1, 1? So if you're trying to be as efficient as possible, plug in 2, 1, 1 now. So if you plug in 2, 1, 1, you get 12 dz dx equals 4 dz dx. It's good to be efficient. Now, I know time was a factor for a lot of people in the first test, plus 1. So I'm plugging everything in right now because my goal is just to find dz dx. Nothing here says I need to find the general formula. So this equals 5. So I'm getting dz dx is 5/8. And when you're setting up this problem, you should already be thinking, okay, I've got part of it. 5/8 x minus 2 plus, and I have one more job. So this doesn't need to be a long problem, but it does require we know our derivatives. So now I'm going to take the derivative with respect to y. So let me erase a few things I've done here, just so we are refocused. Okay, so I'm going to look at this with the idea that there are two variables, and the two variables are z and y. This time we don't need the product rule. But when we go to take the derivative, it's still going to be 12z, but this time it's going to be dz dy equals x squared as a coefficient, dz dy, plus x minus 1 over y. Done. So I did the derivative of all those things. Now I'm going to plug in my points, 2, 1, 1, so 1 for z, so it's going to be 12 dz dy equals 4 dz dy plus x is 2 minus 1. So that looks like 1/8. Okay, I have learned from a couple years of doing these videos, it's good for me to pull up the solutions just in the off chance, I do a calculation error and then students are upset by that. So let's bring up my archive. Right now we're looking at the most recent exam. Okay, it looks like I have that same answer. So let's keep going. Then we have a question. I don't always have this on the first page, but this is actually, so that was a tangent plane question. That was a chapter 4 question. That's mostly testing. I mean, I probably will have something that challenges you on your partial derivatives. This is one common way I do it. So be ready. Let R be the region in the first quadrant bounded by these things. And it gives us a picture. So this is y equals x minus 2. This is x equals y squared. And there's y equals 0. So in order to do this question, you're going to need some intersection points. There's a couple ways you can set it up. But however you do it, and the picture just didn't print off very well. However you do it, you do need to find the intersection of these two things. So we need to combine them. Probably the easiest way to combine would be to substitute this way. So y squared minus 2. So 0 is y squared minus y minus 2. And I think that does nicely factor y plus 1. So I think I'm getting negative 1 and 2. So this must be when y is 2. And the other intersection I can't see because it would keep going, and the picture doesn't say that that's part of what we're dealing with. It's the first quadrant. Okay, so when y is 2, that means x has to be 4. I plugged it into both to check that, so when that's 2. These other points would be good to know. So this would be when this intersects y equals 0, which has to be at 2, 0. And this would be at 0, 0. Okay, so that's helpful. So now, if we're going to do this, there's a clear choice that is much better. And again, it has to do with pattern finding. And when I look at this, it's clear that I would much rather do it vertically. Sorry, that's horizontal, I think. But much rather do it that way. I'd rather do it in terms of y, because the blue is always on the left, green is always on the right. So if I'm doing it in terms of y, then I say, well, the smallest y can be is 0, the biggest y can be is 2. Based off of y, if I start walking, I hit this graph first, which is this one. Then as I walk out, I hit the other graph, and I need it in the y form, so y plus 2. So this is by far the best way to do this problem, in my opinion. So then you'd have dx dy, then you'd integrate from 0 to, you just would compute. This is, there will be some computation. You need to be pretty good at this. The integral from 0 to 2, 2y, y plus 2, minus 2y, y squared dy. So it's the integral from 0 to 2, 2y squared plus 4y plus, minus, apologies. There we go. Minus 2y cubed dy. So then you just keep going. 2/3 y cubed plus 2y squared minus 2/4 y to the 4th from 0 to 2. So whatever this is, 2/3 times 8 plus 8 minus, that's going to be 1/2 2 to the 4th, which is also 8. Oh, that's nice. So it's just 16/3. Done. Let's double check, make sure I didn't do something silly there. 16/3 is what we get. You could set it up the other way, but if you did it in terms of x, you'd have to split it up from 0 to 2. The bottom would be 0, the top would be the square root of x. Bottom is 0, top is square root of x. From 2 to 4, the bottom is x minus 2, the top is the square root of x. Okay, so those we now have encountered two important skills. If I ask you partial derivatives, even partial derivatives with implicit, we want to be able to handle those. If I give you a region, there's definitely will be a lot of this in the test. You want to be very good at this. Okay, let's keep going. Then there's a find and classify the critical points, and then use the second derivative test. So these, you definitely will have this on the test. I would say with this test, you know what's coming a lot more than you did on the first test. That doesn't mean it's easy. It just means you know what's coming, and so you should be ready to go. So because of that, I think time is a little less of a factor. But anyways, remember the key ideas. Factor first. If you can factor, do it. Okay, so this would be minus y equals 0. And then there's two possibilities. I don't know if this is helping you, but x equals 0. And you don't have to write out my tree like I do, but I'm trying to do that to help you. And the whole point is there's two ways the first thing can happen. So then you go to the second equation, you plug in 0 for x, and that's going to give you 3y squared minus 3 is 0. And I think that gives us two possibilities. I'm skipping a little bit just to get us through the video faster, but I see two solutions to that. Then you plug this into equation 2. That's going to be plugging a 2 in for y, so negative 3x squared plus 12. This is actually foundations of solving. So then I'm getting negative 3x squared equals negative 9. So I'm getting x squared is 3. Is that right? So this was negative 9. I moved it over. Okay, so I'm getting x is plus or minus the square root of 3. So from this, the conclusion is from the first branch, I got 0, negative 1, and 0, 1. From the second branch, I got negative square root of 3, 2, and square root of 3, 2. So I got 4 critical points. So we have a little bit of work to do our second derivative test. So second with respect to x twice is 12 minus 6y. With respect to y twice is 6y. With respect to x and then y is going to be x and then y is negative 6x. I'll double check y and then x. Okay. So for each one of these, we have a little bit of work to do to see. So if I plug in 0 for x everywhere, that's going to be 0. And 1 for y everywhere, what I'm getting for d for this one is 6 times, I'm plugging in negative 1 for y, apologies. So if I plug in a -1 for y, and maybe I should choose a different color so I can make this more explicit. And you should probably, I mean, I'm trying to quickly explain in a video, but you should write this clearly that you actually computed d. Okay, so if I plug in the d, I'm getting 18 times -6 minus 0 squared. And all that matters is that's negative, which means this is a saddle. Okay, keep going. 0, 1. So if I plug in 0, 1, the d is going to be 6 times 6 minus 0 squared. That's 36, which is positive. Then you got to look at these. Since both of these are positive, that means it's concave up in all directions, and that means this is going to be a min, a local min. Then we keep going. Negative square root of 3, 2. So if I compute that, plug into d, plug in a 2, I get 0 times 12. And it doesn't really matter what the rest of this is. -6, negative square root of 3 squared. That's less than 0, so that's a saddle. And then lastly, the square root of 3, 2. Same thing, because we're plugging in a 2 for y, d is going to be negative, because you're going to get a 0 for the first part. Saddle. Okay, let's go take a look, make sure I didn't do anything silly. I wrote it much nicer on here, as you can see, but I had a minimum at 0, 1, and then the rest were, so as I said, this was 0. So that's, you should make it clear that you did the second derivative test, and the way you make it clear is you compute the d value. You show me it on the page, don't just do it in your head. Okay, let's keep going. So that's very likely to happen on the test. You do know from doing the homework that there's a few variations, so it's good to make sure nothing surprises you there. Okay, rewrite, reverse the order of integration. This is one way I can ask you about regions. This is mostly about can you graph. So if you don't remember, think of these were my tips in class. Think of these as tick marks, and think of these as the functions. The functions are y equals 2x plus 1 and y equals x squared plus 1. When it's written this way, you should be thinking top, bottom. So whatever you do, you're going to graph these two things. One's a line, y equals 2x plus 1. So a line like this, y equals 2x. You're going to make sure that's on top. And then you're also going to draw this parabola. Now you gotta be a little careful. It hits at 1 here, and it's a parabola that opens upwards. So I think something like this. There's a little bit of work that went into that. Now, if I plug in a 2 to both of these, I think they both give me 5. So that's not a bad thing to do to plug in. When you plug in a 0, they both give you 1. So it is this region. Okay, now I'm ready to reverse the order. So now I'm going to think about it the other way. So if I call this y, and I start to go, okay, this is the left, this is the right. What's the smallest y can be? Well, we just said that was 1. When you plug in a 2, we just said that was 5. So now we're all ready to go. From 1 to 5, I need to know what this is and what that is. X equals what? X equals what? Well, this is from the line. That's the lower bound or the left bound. So it's going to be y minus 1 over 2. And then I need the other one in the x equals form. So it's going to be y minus 1 is x squared. And this is going to be the square root of y minus 1. And then g. I think what happens sometimes is people think because this is the bottom, it's going to have to also be on the bottom when you flip. But no, this is larger. This is a bigger x than this one. So it's left, right. Okay, there we go. 2 parts below are not related. I didn't check that one, but that was a setup. Oh shoot, that's a different question. Apologies if you're looking at this. It looks like I changed the version slightly between the tests. So I'm sorry, I just did a little different problem. Oops. I think that I said I probably changed the version. Didn't post the right version, but you got some more practice there anyways. So hopefully that was helpful. Okay, let's keep going. Consider this region R in the xy plane that is inside the circle and above the x-axis. Inside the circle, above the x-axis. Do read carefully. I find that sometimes a problem on the test. Set up a double integral in both ways for this. So this is meant to be a quick understanding question. To me, polar would be the easier of the two. This would be 0 to pi. This would be 0 to 3. This would be sine of r squared, r d theta. And that would be the much easier way to compute that. But if you're doing it in terms of, it says dx dy. So that's saying you're fixing y. And based off of y, what is this? And what is this? Now first think about what the biggest y can be. So y goes from 0 to 3. Based off of y, I need to take the equation for this circle, radius 3, so this would be it, and I need to get the left and right sides of it. So I need it in the x equals form. So it's negative the square root 9 minus x squared, square root 9 minus x squared, sine of x squared plus y squared, dy dx. Shoot. I started to, you can see how I caught myself right there. I realized right as I wrote that didn't make sense. The question asked for dx dy. My mistake was I solved for y, but that's how you can catch it yourself. X is equal to plus or minus square root of 9 minus y squared. So I knew the moment I didn't mean to make that mistake, but I knew the moment that these were not matched up right, that I had made a mistake in these bounds, because there shouldn't have been an x in there. And that's how I caught it. All right. Anyways, find the area of the region in the fourth quadrant inside the cardioid and inside the circle pictured here. So this is a polar setup question. You should immediately be thinking what those two angles are. And then for any angle in between, as you walk out, you hit this on the outside and you hit that on the inside. The moment you see that it's area, it's the double integral of 1. That's that application we saw in 15.3. So this question is all about finding the bounds and converting. Now the cardioid's the inside, so actually that part doesn't require any converting. And also we know the bounds. You could do 3 pi over 2 to 2 pi. That would be one way to say it. 3 pi over 2 to 2 pi. Another way to say it was negative pi over 2 to 0. Those both would be fine. I think if I was doing it, I would do negative pi over 2 to 0. Just because I like having a 0 in there. But the outer one we need to convert. So we need to convert x squared plus y squared equals 4. But that's the same as r equals 2. You do have to remember that dA becomes r dr d theta, and then you're off to the races. This is mostly a computational thing. Once we had that set up, negative pi over 2 to 0, it's 1/2 r squared. And I think this was the one place on this test where I was like, okay, here's where they're going to have to do quite a bit of computing. There probably will be at least one integral where you do have to do some computing. And this ends up being 2 minus 1/2 1 plus sine of theta squared. And there's no way around it. We're just going to have to expand. Negative pi over 2 to 0, 2 minus 1/2 1. This unfortunately does happen quite a bit with polar problems. And then you would have to remember, oh no, half angle. 1/2 1 minus cosine of 2 theta. But once you do that, then you're ready to integrate. If it was me, I would take a moment and expand everything out to minus 1/2 minus sine of theta minus 1/2 plus, I'm doing a bit of expanding. In fact, I just made a mistake. And this is me kind of not following my own advice, but this should be here. And there's also this 1/2 out here. So there is some room for computational mistakes. Maybe I can just draw right on top of it. This should be a 4th if I distribute. So I'm going to try to I'll see if I can get away with this. This is a bad example. But 1/4 plus 1/4 cosine of 2 theta d theta. And if it was me, I probably would take a moment and put these numbers together before I integrate. Just so I don't, mess that piece up. So it's the integral from negative. So I've written really sloppy, apologies, explaining along the way. So 2 minus 1/2 minus 1/4. How many 4s is that? This is 2 fourths. This is 8 fourths. So that looks like 8 fourths minus, okay, so 5 fourths. 5 fourths minus sine. This is just from experience. I find that if you're going to simplify your fractions, it's better to do it before you integrate. Then we can integrate. So it's 5 fourths theta plus cosine of theta plus 1/8 sine of 2 theta from negative pi over 2 to 0. I don't know why I started to write 2 there. Lots of problems here. Okay, you plug in the 0, you get 0, 1, 0. So I get 1 minus, so that's what happens when I plugged in the 0. Then we're going to plug in the negative pi over 2. So I get negative 5 pi over 8. And then I get cosine of pi over 2, which is 0. Then I get sine of negative pi over 2 times 2, which is 0. So I get 1 plus 5 pi over 8. Okay, let's go take that. I did a lot of calculation there, so there's a decent chance I've miswritten. Okay, we did that first part fine. 1 plus 5 pi over 8. Okay, we did it. Last question. Oh, it's a box question. Optimization. To me, these are more straightforward. We're going to minimize the cost. So the first thing I would write is cost. The cost of this thing. Well, what does it say? Your job is to design a box. All walls are made of plywood. You're told that the total cost must be this. Total volume must be 6. And that the cost of plywood is $3 per square foot. So $3 per square foot times, it's all made of plywood. Yes. And so this is the box. And so I give the labels. Let's start listing how much plywood there is, how many square feet there are. So there's 3 times xz, 1, 2, 3, plus 2 times yz. There's 2 sides that look like this, 1, 2, and then there's the bottom. That's our function. And the question says we want to minimize our cost, which doesn't make sense unless there's some restriction, because if you want to minimize your cost, you don't build it. The restriction is that x, y, z has to be 6. That implies z has to be 6 over xy, which allows us to turn this into a 2-variable function for the cost. And so we get 3, and then we get 18 over y. I did a little simplifying just now. I put this in here. I'm going to do the same thing here, plus 12 over x plus xy, and then we're ready to go. Okay, so then the rest of the question is the partial with respect to x, which is going to be 3 times the 3 doesn't really matter. This, and then the partial with respect to y is going to be 3 times negative 18 over y squared. And honestly, you should be pretty quick with those derivatives simply because we had quite a few in the homework where we had this. This means that y is 12 over x squared. And we have to plug this into this. Now, I personally have a little plan of attack when I do these problems because I really don't like having fractions inside of fractions. So I honestly like to take a moment and rewrite the second equation without fractions, and then I plug it in. It's just a small thing, but I find that it makes the solving easier, and it avoids fractions within fractions. And I'm like, well, if I can avoid that, I would like to. And then we just need to simplify this. Let's see. So that looks like 144. I'm seeing how far I can go without a calculator. We have an x. We have an x to the fourth on the bottom. We have an 18. So that looks like 144 equals 18x cubed. I did a little bit of simplifying. And so it looks like if I did 144 over 18 and did the cube root, I would have it. So on an applied problem like this, I'm not going to ask that you prove anything about it. I just want you to find it. Now, the question said find the minimum cost. That's not the minimum cost. If you want the minimum cost, you would then, where my mouse went, you'd plug this back in and get your y, and then plug those in and get your cost. Let's just peek at the solutions for that computational part. Oh, it was 2. It was a nice number. See, I was just being lazy. I didn't compute that. Definitely compute it on your calculator. And that gave me a 3. And then I plugged in and I got 54 was the cost. That was a tough exam for students. I think the median was like a 76%. So if you can do that, that's interesting to compare. Let's just, while we're here, peek at a couple other ones. Here's spring 2019. Let's zoom in. So spring 2019 did have a question from 13.4. That last exam didn't, but there's definitely a chance it could have on yours. Tangential component of acceleration. So you'd be doing r prime dot r double prime over this. In this case, it's just saying find these things and plug in 0. So r prime is 1. 2 over t. Oh, okay, I threw in some derivatives. It looks like 3 plus 2t e to the t squared. And you just have to get far enough to compute all your derivatives and then just start plugging your points in. So we do have a little bit of work in terms of derivatives here. This is going to be -2. There will be some derivative challenges on this test, but I think you'll be able to handle it. T squared e to the t squared. So I just did the product rule. Okay, now I'm ready to plug in 0 everywhere. So plug in 0 everywhere, and you get 1, 2, 3 is this first one when I plug in 0. Plug in 0 to this other one, you get 0, 0, and 2. And then we're going to divide by the length of 1, 2, 3. So it's really this fast. It's going to be 6 over the square root of 1 plus 4 plus 9. So it's 6 over the square root of 14. So the bit of care, let's see, that's spring 2019. I better take a quick glance at the exam archive here. Spring 2019. Okay, we did it. Next question is more like this, implicit differentiations. The two variables are y and z. So if you're taking the derivative, treat x like it's a constant. So let's for this time, let's go straight through the steps. If something's being treated as a constant, you write it as a 0. If something's being treated, and there's no other variables in there. If something's a constant, but it's next to a variable, you bring it down. It's a coefficient. If there's no y or z in it, the derivative is 0. If there's no y or z in it, the derivative is 0. Okay, so then we have some more work to do. The derivative, we're treating this as if it's a function of y. So it's going to be e to the 2z times dz dy. And here we're doing it. Now we do need the product rule. We have two variables, first, second. So first times derivative of the second plus the derivative of the first times the second. Done. If I was doing this problem, I then would plug in 1 for all my x's and y's, a half for all my z's, and then I'd have it. Find and classify the critical points. I won't go through that. Evaluate this. This is about knowing what this region is. Y equals the square root of x. Y equals 2. So these are good things to practice. Make sure you're very efficient at this. You can set it up either way. We could do it as the integral from 0 to 2 That's if we're doing it in terms of y. And then you would say on the left is x equals 0. On the right is x equals y squared. E to the y cubed dx dy. That's one option. The other option would be to figure out what this is, which it looks like it's 4. You do the integral from 0 to 4 from the bottom, which is the square root of x, to the top, which is 2. Now, an interesting thing about this question is only one of those is oops, I miswrote there, apologies. Again, this is how you catch your work. You can see how I caught it because that didn't make sense for there to be an x there when that was due. Okay, the main issue is I don't know how to integrate this. And so I would much rather do this. You say, well, why is that any different? Well, if we're integrating with respect to x, then there's just going to be an x here. Then it's the integral from 0 to 2, y squared e to the y cubed dy. And you can do that with substitution. Okay, the first octant. Okay, another volume setup. Double integral r 12 minus 3x squared dA. And then your job is to draw the region. So for these problems, they gave us a y equals 3. And they said first octant. But that did not tell us the whole region. So then step 2 is to find when does this hit the ground in the first octant, intersect your z's, and that would be when 12 minus 3x squared is 0. That would be when x squared is 4, which in this region would be when x is 2. We needed that. That contributed that other side. And now we're ready to go. So it's a double integral from 0 to 2, 0 to 3, 12 minus 3x squared dy dx. That's part of that process. I did that quickly. But anyways, then we have a polar problem. This is about converting. Again, you'll have to remember that this is the same as r squared equals r cosine of theta, which means r equals cosine of theta. And when you're walking out, that's this r. Whereas this r is r equals 1. So again, the bounds for this would be the integral from 0 to pi over 2, the integral from cosine of theta to 1 of 3r r d theta. And then you compute. All right, then there's a global max question. A lot of students have been asking about this in terms of process. The things I really need to see here first is this. You need to show me this work. It needs to be part of your work. And this is more about process. So if you know the process, you can really get a lot of points here. You say, well, that can be 0 when y equals plus or minus 1. And then you plug these in. You say, okay, if I plug in y equals 1 here, that means x has to be 0. If I plug in y equals negative 1, that means x has to be 0. So there's two critical points, 0, 1. And 0, negative 1. And only one of those is in the region, right here, 0, 1. And eventually, whether you do it now or later in the problem, you'll compute the corresponding z value. In this case, when I plug in 0 for x and 1 for y, I get 5. And what we just did is we ruled out everything else that's inside the region. Because if there was a point inside the region where the function had a maximum, it would have been a critical point. And then we're going to go one by one through the sides. Now this thing has two boundaries. It has points that are on this lower half. Maybe I'll use a different color for this. They have points that are down here. And points that are down there are characterized by y being 0 and x being between negative 2 and 2. And notice these 2 points are important. X equals negative 2 and 2 are endpoints. So now we want to study the function at the points where y is 0. If you plug y equals 0 into the function, you get negative x plus 5. I'm plugging that in up here. That's a linear function. So in my solutions, I might say that. But there is a general method. The general method for any one variable function over a region for finding the max and min is to take the derivative, one variable derivative, set it equal to 0. If there are no solutions, great. If there are solutions, you need to consider those. But if there's no solutions, then you only have to consider the endpoints. Now, the endpoints in this case are the corners. You always will end up considering the corners. So from this, we learned there's 2 points we need to consider, -2, 0, and 2, 0. And you can plug those back into the original function, or you can just plug in 2 and -2 here. So if I plug in -2, I get 7. If I plug in 2, I get 3. We're done with that side. And there were no new points we had to consider because there was no place that that one variable function had a derivative that was equal to 0. Okay, so then we keep going. Last side. And so when I'm grading, I definitely want to see this. Particularly, I'm looking for this function. There's a lot of stuff to look at when you're grading these problems. So I go, okay, did they show me that function? So you can do that as well. Lastly, what happens if you have a point on this side? If I have a point on that side, then that means that x squared plus y squared is 4. It also means that x is between -2 and 2 because all the points are. So we need to plug that into the function. There's a couple ways you could do that, but probably the easiest would be to solve for y, simply because the function has a y squared in it. So when I plug that in, then you would have the square root of 4 minus x squared squared. And that's going to give me x times 4 minus x squared. And this is what, once you've done a few of these problems, the beginning stuff we just did goes quickly. And then you have this one part where you have some work to do, plus 5. So altogether, I'm getting z is -x cubed plus 3x plus 5. And I need to find the maximum of that function over this interval. Now, a couple small things. When I plug in 2 to this, I'm going to get 3. When I plug in -2, I'm going to get 7. The reason I know that is because I've already plugged those into my function. So I don't need to plug those in again. The question is, are there any other things from that side that need to be considered? And the other things would be, okay, when is the derivative equal to 0? And if you solve that, you get 2 answers, when x is plus or minus 1. So somewhere on this thing, erase here a little bit, there's 2 points, like right here and right here, where x is 1 and x is minus 1. If you wanted, you could solve for the other point. I think we could deduce what it is. It has to be the square root of 3. It has to be the square root of 3. Because the first one squared plus the second one squared has to be 4. So I did a little bit of solving there. You can either plug those into the original function, or you can plug into what you've already done here. So meaning you don't need to go all the way back. If you want to know what f of -1 root 3 is, you can just put this -1 in here. So you already put in the root 3 right here. And if I do that, I get 1 minus 3 plus 5. So I think I get 3. And then if I plug in x equals 1, I get -1, I get 7. F of 1 root 3 is 7. At that point, I'm done. At that point, we've plugged in 5 points, those 5. And I didn't have to plug in the endpoints again because I've already done it. So the global max is 7. It's the biggest output I can get anywhere in the region. And there are 2 places where it occurs. It occurs at 1 root 3. And what was the other one? -2, 0. So in that test, I explicitly asked for those things. Let's see how we did. And looking at that. Yeah, there we go. Okay, that's a couple tests. I think that's more than enough. I'm going to stop there. Hope that helps.